Aha! Richie, thank you. Richie's got to vote. Well, what the hell? The problem with this is the negatives. The negatives are causing the cancellations. -2 cancels +2. -1 cancels +1. Okay, that's a problem. So just take the absolute value. What do we lose with the absolute value?
The negatives.
And what do the negatives imply to us?
That's lower than average.
Are they below or above average? But that's not that big of a deal, because we still know what?
Just the variation.
Good! We know how far away they are, just not what direction they are. So if we're talking about distance from average, we haven't lost that at all. And I love that. Unfortunately, statisticians do not use, that measure is literally called the average deviation. And it's not used statistically. I got this great, as you know, I post everything on YouTube, people can watch it. And I got involved with this great discussion of a guy overseas about why people don't use the absolute value. And it's a calculus reason for the most part. Mostly it's calculus, because when you have an absolute value function, you might remember this from Math 111, I apologize for bringing back any terrible memories. But the graph of an absolute value function always had a point on it, right? It's always got like a hard turn, like this or like this. Sometimes it depends on what you're absolute valuing, but it might go like this. But they always have hard points. And when you do something called calculus on curves like that, you can't what's called differentiate at those points, which means you can't optimize at those points. So we throw those out statistically because you can't do this one very important thing that you guys don't have to worry about in this class anyway. But I'd rather not give you a tool that nobody uses so that when you do go into the world and have to use it, it's not there waiting for you. Crap! Thank you for the absolute value idea. It's so logically simple. Here's the counterintuitive way the statisticians have gotten away from the... Oh, Austin, what's in your mind? Oh, I thought you just put your hand up. Okay. Here's what statisticians do. They create another column, and they square the results in the previous column, which is nothing I would ever think to do mathematically. Like, why the hell would you do that? Because here's what happens. Look. When you do that, all the deviations become positive, sure. But the true problem I have is that the further away they are from average, the more kind of blown up they get. Now granted, Ernie's are pretty close to average, so he doesn't get blown up too much. But look at Bert's. Bert has one that was, Bert Austin was -20. If I was to do this with Bert, it would be positive 400. That's my first issue. The further away, the more kind of goofy it gets. That's a problem. That's a problem. The other problem is, what's the unit on that compared to the original units that we were dealing with? Some of you guys actually used this word earlier. I was so stoked. 82 what? 81 what? 83 what?
Percentage?
Percentage points. Some kind of point, right? Points. 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 How about these differences?
Those are points.
Those are in points as well. What are they now?
Point squared.
Square points. What the hell is a square point? I don't know what a square point is because it doesn't actually exist anywhere. But this is what you have to do mathematically. If anybody wants a logical... I went back and proved why this works, and I put it on that enrichment page on your website. If you're interested. I predict none of you will be. But if you want to see why mathematically this works, it's posted for you. Okay. So now we have the squared deviations from average in square points. I promise you we'll take care of that by doing what at the end? What will we do at the end to fix that? We'll take the square root to fix it, Jacob, thank you. We'll take the square root to fix that. So we'll come back to that, I promise you. But we can't get the square root right now. If we took them right now, we'd go right back to where we were, essentially. So what do we do now?
Square root of the mean of those values.
Say that again, Jacob.
Square root of the mean of those values.
Good. The thing we have to do next is we have to average those. Now we have a choice. We can median, we can mode, or we can average. But by definition, what happens next is we average these values. So the first thing we're going to do is we're going to sum these bad boys up. Big sigma. Big sigma. Remember what he means? Always? Add. Always means add. And we're going to add these bad boys up. That looks like hell. Looks like hell. Looks like a formula. Don't worry. Don't worry. You're going to do it once by hand. I promise you. Never do it again by hand for this. All this means, though, is you're adding up the squared deviations. That's all that means. So you add those numbers up, which is 10. Boom. Please, tell me your name again, too.
Natasha.
Natasha, go.
Why don't you just take the absolute value of the ones instead of...
The previous.
Yeah.
It's not, the real reason is it's a non-differentiable function.
Yeah.
And because it's non-differentiable, we can't optimize, which means maximize or minimize when we need it to. Now, that's kind of like when you take your cell phone and push the power button, it comes on. We don't really care why, we just know it does. Does that make sense? Right? I mean, like if your cell phone's on the fritz, generally you don't try to take it apart and fix it yourself. I wouldn't, personally. You just know that when you push the power button, it comes on. When variation is measured in the world, the absolute value function is not used. This one is. And that's a terrible reason. But the mathematics behind it, if you want them, are online for you, I promise you. I promise you. But I've learned from years ago not to explain it in class because it's a guaranteed way of putting you all sound asleep within 10 minutes. But it's hidden out there if you want it. Non-differentiability. Have you taken calculus before?
Yeah.
The fact of derivative not existing at a corner point is the main reason we don't do it that way. And if you want more, it's online for you. Wait for you. Cool. Great question. Fantastic question. It's a much more logical step to do. And here's another illogical step. Jacob correctly said we are then going to average this. Now, I'm going to introduce a term here. It's called the sample variance. This is a formula not to be memorized. It's going to be used right now, but not memorized. I don't want you memorizing formulas in this class. Well, two. I want you memorizing two. You already know one of them anyway. The sample variance is essentially the average of the squared deviations. So these are the squared deviations. If you average them, you get what's called the sample variance. That's just a statistical definition. But here's the slightly confusing part. You take the number you just came up with, which is the sum of the squared deviations, and Jacob's going to say, you average them. Logically, you would divide by, in this case, what? Exactly. Here's the slightly illogical part. You actually divide by 1 or less. Don't worry yourselves as to why, because this is the only time you'll actually do it by hand. Technology will take care of all of this for you from now on. If you want a reason, where's the answer? On that enrichment page. There's a great mathematical reason. It's actually freaking gorgeous. But none of you care. I shouldn't say that. Some of you might care. Most of you don't care, though. And I'd rather not teach to 1 or 2 people that actually do care. It's there waiting for you if you want to see it. That's called the sample variance. That's how you average. You average it with 1 less data point than you actually have. Which, as the data set gets larger and larger, doesn't matter anyway. Don't worry about why, unless you want to see why, then go online and check out that little derivation. Let's just use our numbers and get this guy now. What's the sum of our squared deviations? It was 10. N minus 1 for us is actually 4. Yeah, it's 4, 1 less than 5, which is 2.5. Problem. Still, 2.5 what?
Whatever.
Points squared. John, go.
Where did you get the 5?
The 5, no, great question. It's how many data points you have.
Okay.
We had 5, it's 4 because it's 5 minus 1, but that's where the 5 came from, friend. Great question, fantastic. But what's the problem with 2.5? It's squared points, which is meaningless. So how do we fix that? You take the square root. And this is the important measure. Jacob, you mentioned this about an hour ago. It's called the sample. Make sure the camera's actually pointed in the right place right now.
That's right. Yeah.
Is it okay? Good, thank you guys, thanks. It's called the sample standard deviation. This, and Natasha, coming back to your awesome question from before. This is the king, queen, jack, jester, squire of statistical variation measures. He's the one that actually gets used because of the fact that you can differentiate a parabola, but you can't differentiate a corner point. Fair enough?
Yeah.
Fair enough for right now. This guy's so important he gets a letter. We call him little s. We call him little s. And all he is the square root of, oh, that's population. We'll come back to him. I know why you're dealing with him in physics, because you deal with thousands, if not millions of data points. When you have small data sets, you gotta call them S. We'll come back to why. Little s is your sample standard deviation. And all this guy is a square root of whatever that sample variance is. It's a square root of that sample variance. FYI, this is the only time you'll ever use the sample variance in this class, was to get this guy right here. So it's the square root of 2.5 points squared, which is 1.5-ish. 1.5, I call that 1.58, thank you Nathan. 1.58, what?
Points.
Points. And now we're happy. A, because we're done. A, because we're done. But B, because 1.58, the unit agrees with the average. Now, let's take a deep breath.
So that means,
Oh, this is the important thing, Lauren. What does it mean? Go ahead. What's on your mind? What's on your mind? That means...
that Ernie's,
I love where you're going with this. No, say it, whatever's on your mind, because I think you're looking in the right place, sister.